detect a thermal anomaly at a volcano that we don't expect, then we start focusing all of our energy and watching that volcano as acutely as possible, and eventually you'll have something like this. Although this is a different volcano, this is Klishcheskoye and Kamchatka Peninsula. It's a typical plume eruption coming out of that volcano. The other thing you have to watch for is, I want to explain this definition. Here we're looking at a plume. This is attached to the volcano, but eventually the volcano stops erupting, but it still has this drifting material going downwind, and we refer to this as a cloud, in this case an ash cloud. Could be a volcanic cloud or an eruption cloud is often used, but this case is very specific as an ash cloud. I'll talk about that in a bit. These are examples of what some of these plumes look like at the various wavelengths. You can see there's very distinct physical characteristics, and there's actually some chemistry going on that we can work with, but I'm afraid that's going to be down the road a ways when we get some better spectral data available. That's what it looks like in the visible, near infrared, or red visible, both. This is an interesting channel. This is the 3 to 5, or 3.5 to 3.9 micron range, and it detects hot targets, but it also detects visible light. So it's a kind of a crossover channel. It gets very complicated to analyze some of that data. But we use it a lot, especially for really hot targets. So when you get out here in a long wave IR, the plumes show up very distinctly, very dark, very cold. Okay, another thing in analysis that we have to watch for is there's an evolution as this cloud develops and starts to drift. So initially we have a plume. It's an opaque cloud right over the volcano. You can see it expanding and growing and drifting. And then down here, you see it's starting to disperse. And once it starts to disperse, we can't get a clean signature off of it as we do in a single thermal infrared channel. Now, what happens is, as this thing starts to disperse, you have energy being reflected up through the cloud from the ground, so you can't get a consistent temperature off the cloud because you're looking at readings from the cloud and readings from the background, and the combination of those two pieces of information, it's not giving you anything of any value to yourself. However, what happens as that cloud disperses, when you take a look and subtract the two long-wave thermal infrared channels, that's 10 to 11 microns and 11 to 12 micron, turns out there's a significant difference in the absorption of silica in those wavelengths, and versus weather clouds, which weather clouds don't really have an effect on this wavelength. So by subtracting those two channels, well, here we have an opaque cloud. We really don't see much showing up in this thing. Here we have this drifting plume, clouds gotten away, and in this split channel, we're starting to see evidence around the edges. Okay. So in the center, where it's opaque, we're getting a temperature off the cloud, which helps us derive or estimate the cloud height. But around the edges, this is where the background radiation is coming through the cloud itself. It turns out there's absorption differences of silica at the two wavelengths, as I mentioned, and by subtracting those, you start to bring out where the silica is and where it isn't. Now, you're not seeing it in here because there's no radiation coming through the cloud. But you get down here where the cloud is a few hours older, you get a full cloud of mapping the silica content. And of course, the silica content is volcanic ash. Another thing we've been able to accomplish over the years, and this is kind of what I'm leading up to some things that we can do with the data. We've been able to track these clouds. Because I told you about high temporal resolution data, you have data coming in every half hour, every hour, GOES or AVHR, and you can track the movement of these clouds. And this cloud is from Spur Volcano. It was tracked out of Alaska, across Canada, into what we call the lower 48, across the Great Lakes, and now it's all the way up to Greenland. And we've seen some of the other data sets that have crossed over and over Europe from some of the more recent eruptions. Now, I told you about the split window signal. We have an assumption that wherever the strongest signal is occurring, it's also where the highest concentration of ash. The problem is it's never been measured. It's never been quantified because these clouds are, they're drifting, they're changing, they're evolving. And to get a sampler up there to sample these things and find out what's going on, it can be very difficult. The most recent eruption in Iceland, because of coming over Europe, we had some of the British aircraft were up to take samples, some of the German aircraft were up to take samples. So we're going to learn a lot about these things because of that eruption. The other thing, the problem is because that radiation comes through it has to reflect off the ground or be radiated by the ground rather, through the cloud, any differences in the ground environment changes that spectral signature. So it isn't always a consistent spectral signature. I mentioned getting the temperature of the cloud. This one was at, I can't read that, -65°C. Well, at the same time, real-time satellite data isn't the only thing we need. We need real-time other data sets. This is a real-time wind field that we collect every 6 hours. It comes in every 6 hours. It's modeled and forecasted every 15 minutes for that 6-hour period. Using this data, we look at the temperature profile of the atmosphere. -65 is right about here. We follow that up to see where it crosses the profile of the atmosphere, and you see it crosses it right at, what is that, about 14 kilometers? 12 kilometers, right about 12 kilometers. So that gives us an estimate. At 12 kilometers, the temperature matches the temperature of the cloud. So remember, it's this hot cloud. Initially when it's hot, it erupts. As it rises through the atmosphere, it cools and cools and cools until it arrives at the temperature of the surrounding atmosphere, and then it stabilizes and spreads out. Now, it doesn't always arrive perfectly. Sometimes it overshoots, super cools up here, and there's other problems with this technique. But basically, these are the ideas, and it works fairly well. This was an interesting eruption. This is Cleveland volcano. The initial analysis of the satellite data only detected this cloud right here. The volcano is right about here. And that's at a band 4. And so that gave us a temperature of that cloud. But then, just out of curiosity, we took a look at the split window, or ash band, and sure enough, there was a second cloud going in the opposite direction down here, showing up in the ash band. Well, we did a profile of the atmosphere to take a look and see what's going on. Here, the wind's blowing to the northwest. Was at above 7 kilometers. And in this case, this thing had -53°C and actually matched the profile of the atmosphere. And everything below 7 kilometers was blowing to the southeast. So we knew we had a wind shear that was splitting this cloud. And that helped us define the altitude of the cloud as well. Okay, thermal anomalies that we often detect. I mentioned about them before. This is a forward-looking infrared radiometer. It's essentially a thermal camera. Looking at the hot vent from this eruption. This is a lava flow. This is what it looks like on satellite data. Remember, satellite data gets saturated at a certain level, about 60 degrees, maybe 50 degrees, depending on which of the NOAA satellites you're looking at and how old it is. And so, lava flows are, 1,000 degrees, let's say, so you're not detecting the actual temperature. But for something to saturate a satellite, a 1 kilometer by 1 kilometer pixel, to saturate that takes a lot of energy. And these got saturated, and these get saturated a lot. Thermal anomalies, it's not unusual for them to get saturated. We can tell when they're saturated because there's a recalibration pixel that follows right here, which is very, very cold, being off the cold scale of the sensor detector. And it's very important to us because the only thing that results in really hot targets like that are lava flows and certain forest fires, and certain parts of forest fires. So that gives us some information about the fire. And then, of course, we get a pixel count. The other problem you got to worry about is, make sure your geometry is good, because sometimes you look it off to the side, and when you reprocess the correct geometry of the data, sometimes it fills into reprocessed extra pixels. Okay, so another data source. Now remember, real-time data alone doesn't always solve your problem. So here we use real-time data. We looked at the wind fields, looked at the temperature profiles. We get them coming in real time. We also use that same global gridded wind fields to run a dispersion model. So we use a global gridded wind fields that are currently received over networks. Okay, so what we do is that we do this on, we don't even use a supercomputer. We didn't want to use a supercomputer in this modeling. We release hypothetical particles in a computerized atmosphere, which is based on the real atmosphere data coming in. We release these particles in a wind field, and we track the movement of these wind fields as the particles blow through the wind. And when you do that, you end up with an image that looks something like this. I'll show you an animation of what it looks like in a few minutes, but this is something I wanted to point out. Okay, so here is the SCOES satellite image of this eruption. Now these are multi